This video is the second video on hypocalcemia. So the first one is chronic renal failure, and this is specifically chronic renal failure in non-horse species. And that's again because horses don't need vitamin D for intestinal absorption of calcium. Horses readily absorb calcium from the diet. So with chronic renal failure in non-horse species, there is a decreased renal functional mass, and the kidneys normally have an enzyme called 1-alpha hydroxylase. And with a decreased functional mass, they have less of this enzyme, so there's less 1-alpha hydroxylase. And this is the enzyme that converts vitamin D to its most active form in the body. So with less of this enzyme, there's less active vitamin D, and then that leads to less intestinal absorption of calcium and hypocalcemia. So that's the first mechanism with chronic renal failure. There's actually another mechanism, and that is when there is a really high phosphorus concentration. So the phosphorus is high because there's decreased GFR. Phosphorus is a uremic acid, so it's normally excreted by the kidney. But when there's decreased GFR, there's less excretion of phosphorus, and phosphorus remains in the blood. And when it gets to a high enough concentration, it can precipitate with calcium, so it can spontaneously bind to calcium, and this is called metastatic mineralization. So calcium times phosphorus greater than 70, it sets up this wonderful environment where they'll spontaneously bind and precipitate out of solution. So those are the two mechanisms for chronic renal failure. The next cause of hypocalcemia is hypoalbuminemia, or a low albumin concentration. And to explain this mechanism, I'm first going to draw the normal fractions of calcium in blood. So about 50% of calcium is the ionized calcium, and that's the metabolically active form of calcium. But 40% is protein bound, and specifically bound to albumin. That's the major component. And then 10% about 10% is non-protein bound. So with hypoalbuminemia, there's a decreased concentration of that protein-bound form. But again, that protein-bound form is not the one that's under metabolic control. It's the ionized form. The ionized form is still at a normal concentration, so it's not a true hypocalcemia. The total calcium is decreased, but the ionized is normal, so just keep that in mind. The next mechanism for hypocalcemia is lysis, and that is rhabdomyolysis, what we're going to be dealing with in this class. And you already learned about rhabdomyolysis in the hyponatremia, so if you want to revisit that, you can certainly do that. So the next mechanism is a inappropriate use of an anticoagulant. So with our serum chemistries, we use heparinized plasma, but sometimes the plasma is inadvertently obtained in the wrong anticoagulant. So specifically that's EDTA, so this is an in vitro binding of calcium to EDTA, and that will cause a very severe hypocalcemia in vitro, not in the patient. And the one thing that should key you into this mechanism is that the hypocalcemia is not compatible with life. So you'll get the result back, and the animal will not be showing any signs of hypocalcemia. So again, that's an in vitro artifact, and some EDTA also contains potassium, so you might also get a marked hyperkalemia that is again not compatible with life. So the next mechanism is intestinal disease or decreased intake. So if there's less calcium in the diet, if the patient is anorexic for a prolonged period of time, or shorter periods of time if it's a horse, or any kind of diffuse or generalized GI disease, that would cause decreased intestinal absorption of calcium and then hypocalcemia. The next mechanism is union with phosphorus, and that is going to be metastatic mineralization. So you've already learned about metastatic mineralization, but just to review what it is, it's when there's a really high phosphorus concentration. And that phosphorus then spontaneously binds with calcium and causes hypocalcemia. So again, calcium times phosphorus greater than 70. And we most commonly see this with chronic renal failure because there's decreased excretion of phosphorus. But you can also see it with toxicity. So the animal has been given a phosphate enema that contains lots and lots of phosphorus. So again, that product, calcium times phosphorus greater than 70. And now the last mechanism for hypocalcemia is that associated with maternal processes, so either during pregnancy or lactation. And when this occurs, it goes by various different disease names depending on what animal you're dealing with. So in cattle, it's called milk fever. In dogs, it's called eclampsia. And in cats, it's called periparturient hypocalcemia. But in any case, there's increased utilization or excretion of calcium. So there's lots of calcium utilization by the fetus, or there's lots of excretion of calcium in the milk. There's also lots of utilization of phosphorus or excretion of phosphorus, so you can oftentimes see hypophosphatemia with this maternal associated hypocalcemia. You might also have hypermagnesemia, and I'll talk about that more in the magnesium lecture, but I'll just note here that this hypermagnesemia is helpful in differentiating milk fever from grass tetany, which I'll talk about in another video. And then finally, the animal might also be hypoglycemic if the fetus is using a lot of glucose, a lot of energy, or if there's a lot of glucose excretion in the milk.